Okay, I'd like to hear from us. Okay, I'd like to hear from a few of us, majorly where you're picking us from. Just feel free to unmute and you tell us where you're picking us from this lovely evening. And maybe you tell us more about you and structural design. How good are you in structural design? How do you have that experience? Which kind of codes do you use to design? Do you use Eurocode? Do you use BS? Do you use Indian standards? So those are the kind of things. And majorly, you as a structural designer or someone who is here with us today, just let us know which is that software that you are actually good at in structural design. That's when you add on this robot structural analysis, it would actually be a plus to you. I open up the floor to any of us who is willing to share with us. Just tell us your name, your country, and share with us a few things here and there. Anyone to take
Good
it
evening,
away?
colleague.
Good evening to you.
I'm Katanga. I'm from DRC, Congo, but I reside in Johannesburg, South Africa.
Okay.
I hold a bachelor degree in civil engineering, and I'm working as a structural engineer. So gonna be my first time to use a robot. I usually use Procon to design. That's gonna be my first time to use robot. And
Okay.
in South Africa, we use BS and SANS, South African National Standards.
Okay.
Thank you.
Thank you so much, engineer, for sharing with us. I'm so happy to have you here, and I'm sure
Thank you.
you'll get to learn a lot from today's session. Thank you. Okay. Anyone else to share with us?
Hi guys.
Hello.
Yeah, I'm civil engineering student from Alzi University, first year student actually. My name is Pangayo Lukosi, and the building codes which we practice in our country is British Standard, BS Standard, or 8110. And sometimes we apply Eurocode standard in some cases. And
Okay.
the software that I'm familiar with is Porter software, which usually most of people we use in our country. But I have some simple knowledge on robot software, so this
Okay.
is kind of thing that I want to learn.
Okay. Thank you.
Hi,
Thank you so
everyone.
much. Hello, Talaini.
Taliani.
Taliani. Oh,
Yes,
nice one
yes,
there.
yes. My name is Eileen Taliani. I am from Kenya, Nairobi. We use Eurocodes. I recently graduated. I graduated last year, and in our office we use Excel sheets to design, and we also use Procon. So for the Autodesk Robot, I'm not very familiar, but I'm very excited to learn about it. Yeah.
Okay. Just a quick one, engineer.
Yes.
What's your passion in structural design and structural engineering?
Currently, my greatest passion is digital engineering, whereby like I'm very interested in clash detection. That's my
Okay.
passion currently. So
Okay.
I'm really working to learn the softwares as fast as I can, so that I can be able to get that.
Okay.
Yeah.
Thank you so much. Thank you so much for sharing with us. We are so delighted to have you here with us, and you're in the right place. Thank you. Let me hear from some other person. Anyone else to share with us?
Hello, everyone.
Hello. Let me get Diali first.
Yes, good evening, engineer and the
Good
team.
evening.
My
Good
name is
evening.
Ntulume Diali, and I'm in Uganda. Um, in Uganda, we normally use Eurocodes for designing, and I'm familiar with robots somehow. I've ever had some YouTube videos, and when I try to relate it with Rivet, you find that somehow, somewhere, they try to be somehow related since they are all Autodesk softwares. But at least I'm also more eager to see that I get more about robots such that I can start using it.
Okay. Thank you
Yeah,
so much,
thank you.
engineer. Yeah, thank you so much. I'm as well hosting from Uganda. So much happy to hear from Uganda as well. Anyone else?
Yes, good evening.
Good
Yes,
evening.
good evening.
Good evening to you.
My name is Bagaya Henry, and
Yes, Henry.
I'm Bagaya Henry, and I'm coming in from Uganda. I've used robot structure analysis software before, and for the design of steel structures. Yeah, and I've not used it for design of concrete structures. And yeah, I'm also really so passionate about structure engineering and as well as design of connections. Yeah.
Okay. What, Henry? What is it that stood out for you in your use of robot structural analysis in the due course of what you have done so far?
What stood out for me is the fact that it gives you that kind of it's a bit flexible that it allows you to define your own parameters in a way that you may want other than other softwares that could be limited. Yeah,
Okay.
that's what stood out for me.
Okay. Thank you so much, Henry. Thank you so much for sharing with us. We are so much happy to have you as well. Okay, let me hear from two more people so that we can kick off. Hello.
Hello.
Okay.
Hello. Good evening
Yes,
from
Philip,
Nigeria.
good evening.
Yeah. So I see that a lot of people are you know, talking from East Africa. Decided to say, no, we have to represent. So
Yes,
this is
yes,
Philip
yes.
from from West Africa, Nigeria. I'm
Okay.
a civil engineer. I have close to 15 years of experience. In fact, I would say I started with Excel sheet and designing some years back. Uh, at some point also I switched into another side of engineering, not software related. So now I have a consulting firm. It will be interesting also to see what has changed over the years since I left design. Um, Thank you very much.
Thank you so much, Philip. We're happy to have you here. And I guess we shall grasp a lot from your well of experience as well. Thank you.
Thank you.
Yes. Anyone else?
Yeah. Hello, everyone.
Hello, Kelvin.
Okay. My name is Kevin Karanja. I'm from Kenya, Nairobi. Currently, I'm a graduate civil engineer, and I've never used Autodesk Robot. That's why I'm here. Majorly, I
Okay.
use EDABs. I'm good in EDABs actually to design with it, but
Okay.
it would be helpful if you, okay, for the meantime, you can take us on how to get MEP crash detect. If you know that, it would be helpful.
Yeah. Thank you so much, Kelvin. I'm happy to hear from you. And thank you so much for joining us for today's class. I'm sure you'll learn a lot. You'll get something new to add into your well of knowledge and skills that you have. I see Katanga.
Yeah, sorry, I just want to request if you can please record this session, and then there's a way that I can be coming back and watching it. And
Yes, yes. This session is being recorded, and the recording will be shared tomorrow. If
all right,
you
thank you.
if you signed in for the course, I'm sure you'll actually get the recording. Thank
All
you.
right, thank you so much. Thank you.
All right. Let me hear from one last person so that we can kick off today's class. Anyone?
Good evening.
Hello, engineers.
Hello, Clyde.
Hello, how are you?
I'm doing well. How are you doing?
Good. I'm Clyde Msiwa from Zimbabwe. I have no experience on a robot. That's why I'm here. I only have experience on a contractor who is working on bridges. So I want to learn
Okay.
on robot.
Thank you. Thank you so much, Clyde. Your name seems familiar. You're actually in the Roads Hub community. Thank you so much for joining us here again.
Okay, thank you.
Okay. There was one other person who wanted to share with us before Clyde.
Yes, hello.
Yes, Brian.
Yes, how are you?
I'm doing well. How are you doing?
I'm doing good. My name is Brian Kimanthi, a civil engineering graduate from Wote, Makueni County, Kenya. And I'm quite excited to be here. I joined your last session for Revit as a one-day sprint, and it was quite informative, interactive. Why I'm here today is because I've not used robot analysis software anywhere. So I'm excited to know about it, to learn about it. I've only been using data structure in my analysis of concrete structures. Yeah, and I'm thrilled and very eager to share with fellow engineers. Thank you.
Okay. Thank you so much, Brian. Thank you so much for joining us from Kenya. We are so much happy to have you. With that, those were the few that we could share with today in our interactive session. And once again, in case you've just joined in, I want to welcome you once again for this very lovely 2 day sprint for structural analysis using the robot structural analysis software. We shall be going through from the very onset of modeling. We shall go through to the analysis, shall go through the design, and I'm sure by the end of this 2 days work, by the end of this 2 days sprint, you will be in a very good position. You will have learned the workflow of how to use robot structural analysis, and with that, you can actually apply it to your other works. You include it into your workflow as well. I want to welcome you to Roads Hub. This is Roads Hub. It's a place where we groom ultimate engineers, and I'm so happy to have you here today, and we look forward to engaging more and more. Okay. With that, I would like to welcome our facilitator for today. Are you in a position to take it away, Engineer Gatimo?
Hello, dear gracious. Yes, I am.
Okay.
Am I audible?
Yes, you're audible. Take it away. You're welcome.
Super. Super. Thank you. Thank you so much, dear gracious, for running the interactive session for us. I will also start with or by thanking everyone for taking your time and energy to join us for another session. And it's always an honor, to ask people to join you for a session, and you have people from all around the world or all around the continent joining you and getting to interact and probably just listen to you. And it's something that we do not take for granted, and we are really, really grateful for that. Okay. For those, I can see most of us are familiar with the Roads Up community. I can see most of us, at least we have engaged somewhere. But for those who are new to our community, this is an open space for you to learn, build, connect, innovate, and grow confidence in your skills. We really, try to grow with you, learn with you, probably educate you in the areas that we can, and also encourage you to try and educate others in the areas that you can, so that we can all say participate in growing the engineering fraternity or community, just step by step, or everyone playing their small role. All right. So welcome once again. And my name is Gatumo Ithaka, and I'm going to be your facilitator for today's session. So the sprint is a 2-day event. And today is going to be the very first day of the event. And we are going to proceed to finish it tomorrow. And we have divided it into, say, 2 parts. Today's session will majorly focus on starting the project, and tomorrow's session will majorly focus on the analysis, design, and interpreting the results, part of the design. All right. So the reason we needed to have a 2-day session is this. design typically involves more. You need to have background knowledge or information before you can do your design. All right. And it was kind of impossible for us to fit everything into one session without rushing it through. So we thought it wise to just say separate it into two sessions and then try as much as possible to provide you with more quality or more with more quality during the two sessions. Okay. So for today's session, as I said, we are going to majorly focus on starting the project. And before we start the project, we need to say understand a few things, or probably just familiarize or say take more of a refresher on some of the concepts we covered during our undergraduate studies. And then from there, we are going to migrate to the software. All right. So for probably the first 20 minutes or so, I won't be in the software. And then from there, I'm going to go into the software and take you through what we have for you today. So also this is going to be a very interactive session. We really like say interactive participants so that the sessions do not be very boring. And also considering it's a weekend, we need to say make it more of an entertainment rather than just a purely say a pure lecture. Right. So with that, I'll share my screen. And if you can see my screen, please type a one. Let me know that it is visible. Let me know my screen is visible. Let me know that my screen is visible. Okay, thank you. Does anyone have an issue with how audible I am? Am I audible enough? Someone please unmute and confirm that I am audible enough.
Yes, you are
audible.
very audible.
Super. Super, thank you. So today is going to be the very first day of our sprint, and we are going to start with just giving you a general flow of the sprint. So we have 5 steps that we would want to cover with you. The first one is to introduce you to, say, structural design. And for the sprint, we are going to be focusing on RC design. And I'm saying introduction because I'm assuming that we are, say, new to design, especially with the software. I want to say we are all new to the design, but we have some background information from our undergraduate studies. So after the introduction, we are going to go into modeling. And in the modeling phase, we are going to be majorly using the software. Then from the modeling, we are going to go into loads and load combinations, then analysis and verification, and then production of design reports. So for the very first 2 steps, we are going to do today. And then for the last 3 steps, that is 3, 4, and 5, we are going to do or focus on that tomorrow evening. So if you'll be free tomorrow evening, please feel free to join us tomorrow as well. So let's get started. Uh, I will start with introducing our robot structural analysis software. It's a very beautiful software. It's a software that I've, say, grown to love. I know most of us have probably not interacted with it. And for those who have, say, tried to learn it on their own, may have encountered a lot of challenges with it. And most people end up not taking it up. But it's a very, very good software, and it is quite versatile. I think it's one of the most versatile tools that you're going to find out here. All right. So when you're using a robot is versatile in this nature. It can be used for the design of say, different types of structures. It can be used in the design of steel structures. It can be used in the design of concrete structures. You can use it for design of timber structures as well. And then the software also allows you to define your materials. So if you are not using the typical materials, that is steel, concrete, and timber, you can also define the materials. Say you have the behavioral characteristics of, say, something like bamboo, you could also input them into the software and use them for design as a special element. And then apart from the typical structures that are buildings, it can also be used for the design of bridges and other infrastructural projects that are just are purely structures. Okay. And then it has some interoperability with other BIM softwares, especially the ones from Autodesk, that is Revit and Advanced Steel, and also AutoCAD. So with interoperability, we are talking about you being able to move the models or information from one software to another. So if you've worked with Revit, what this means is you can model in Revit, and then when you want to design, instead of you coming and remodeling from scratch in Robot, you can just transfer your model first, convert it into an analytical model in Revit, and then open the analytical model in Robot so that you can design it. Then after you have designed it, you can take it back to Revit for documentation or detailing, so that you reduce the amount of effort you have to do. And then you have Advanced Steel. Advanced Steel is majorly for steel work. So if you want to do your detailing or you want to do your connections in Advanced Steel, you can do that and then work with both Robot and Revit to make your work a bit easier. All right, so majorly that is a software. And as I said, it's very, very, say, versatile or dynamic, and you can use it for the design of so many types of structures. All right, then after that, I'm just going to go now into the basics of what we are going to be doing. And this is where we are going to be focusing on what we did in our undergraduate studies. So at this point, I think we are all on the same page that we are here in the sprint to design an RC structure. Okay, that is a reinforced concrete structure. So the purpose of designing is so that you can be able to get information that is going to be used in the construction phase of your structure. But even before you get to design, you need to understand what the design typically is and what the analysis is. All right. So analysis is what comes before design. And in analysis, you are trying to predict how your structure is going to behave when it is exposed to the various loads that you anticipate it to be exposed to in the design life. All right. So here you're talking about the loads that your structure is going to be exposed to. So you have your wind loads, you have your dead loads, you have your live loads. They are all going to have an impact on your structure. So I'd say from, say, basic physics, you know that for every action, there's always a reaction. So basically, that's what is built on before we even get to determining how the members behave. So if you have a load, you need your structure to be able to support that load. And that is what we find out in the analysis. So we get to find out that for the live loads that we are, say, modeling on our structure, what moments are they going to cause? What are the shear forces that are going to be generated from those loads? And then once we identify those loads, once we get to know how our structure behaves, then we can move into the design phase. So in the structural analysis, you have identified the internal forces, and you can now be able to tell the kind of deformations and displacements that your structure is going to be, that you expect your structure to have. All right. Then from there, you can now move to design. And in design, you are going to be basically identifying the appropriate sizes and quantities of reinforcement. So you are going to be doing this. So before you do your analysis, you have, say, made a conceptual model. You say that for this span, you probably need a beam that is this deep and has this width. So in the design phase, you're getting to making sure that that cross section is actually appropriate. And then if it is appropriate, what is the quantity of steel that is required for the for the tension, for the compression if it is going to be facing compression, and also the number of stirrups and the sizes of the bars that are going to be required for the shear forces that are going to arise from the structural analysis. All right. And then it is that information that you get from the design that is going to be used in the detailing bit of the design process. Okay. So this is just to say repeat on what we have just said. So structural design is the process of determining a reliable structural system, selection of suitable materials, and determination of optimum member sizes for the structure to be built. So at this point, you have done your analysis. You can quantify the internal forces. You can quantify the moments. So at this point, you just want to know what are the optimum member sizes, what are the appropriate materials. Do you need class 25? Do you need class 30 for your concrete? This is what you get to determine in this structural design phase. Okay. And the goal of structural design is to ensure that your structure will perform satisfactorily during its design life. All right. So I hope you are together up to that point. I hope you are together up to that point. Okay, so I think we are together, so we can proceed. But before we even talk about the design procedure, I'd like to talk a little bit about concrete. So we know concrete is more consists of two materials, or reinforced concrete consists of two materials. It consists of concrete, that is the cement, the fine aggregate, and the coarse aggregate. And then it also consists of steel, or the steel bars. So concrete in itself, it's good in compressive forces, or it can stand high compressive stresses, whereas the steel bars can withstand high tensile stresses, and it is also quite ductile. So these two materials, when they are combined, they form a very formidable building material that we call reinforced concrete. And this, I think, it's one of the most, if not the most, uh, common building material. Okay, it's common because of its, say, affordability and how easy it is to use. You can see, even say, from the areas we stay in, you can see there are buildings that have not, been engineered and they still exist. That's how easy it is to use reinforced concrete. It's one, I think, of one of the most easiest materials to use, and that is why it is, say, the most common use. All right. So with that, we are now going to go into the design phase, and in the design we have several aims of design. So before you start any procedure, before you start to do anything, you definitely have something that you are aiming for. So the whole purpose of you, say, taking your calculator, the whole purpose of you getting to model the structure in a finite element analysis software is because, number one, you want to ensure that your structure is going to be safe and reliable. All right. So as the engineer, you're going to be tasked with ensuring that the structure is going to be safe and reliable. That is, it is not going to fail under, say, the ultimate limit loads that it's going to face. And then number two, it is not going to deform in such a manner that it's going to hinder the usability of the structure. Then number two, your role as the engineer will also to ensure that your structure is fit for purpose. All right. And when it comes to fitness for purpose, we are talking about the arrangement of spaces and ensuring that how you place your structural elements complement the intended use of the structure. So here we are saying that if you place or you choose to place your columns or your beams on the structure, how you intend them to be constructed, they must complement the use of the structure. Okay, so I like giving this scenario where you have, say, a ramp in your structure. You cannot go and place a column passing through the ramp because it is going to negatively impact, or it's even going to totally hinder how that element is supposed to be used. So a ramp is supposed to, say, control the flow of traffic. It is supposed to give accessibility to certain parts of the structure. If you place something or a structural element that hinders that flow or that negatively impacts it, then having that element there is counterproductive. Your structure may be safe. It may actually be safe to be used. It may not fail during its design phase, but or its design life, but it's not going to be usable. All right. You can even say give a more simpler, a more simpler example. You may have, say, a beam running through the living space or the living room. That beam is going to be hindering how light is propagated within that space, and it may not be aesthetic. So people may live there, they will live there safely, but the room is not going to be used as it had been designed for by the architect. Okay, so those are some of the things that you have to consider. You have to ensure that your structural elements, even before you get to design them, you consider how they are going to be, say, existing or coexisting with the other elements of the structure. We're going to talk about that more in a few once we get to the modeling space. Then the other aim of doing your structural design is designing for economy. Okay, so when designing for economy, we want to ensure that your structure is economical to design. Remember, uh, the built industry is one of the largest sources of pollution. So if we say proceed to design and economically, we are also adding the pollution, and it's actually it's a negative thing. Then, so when it comes to economy, we are saying this: the design should be, say, economical. The factors of safety that you're going to be providing, they should not be so generous such that the cost of construction becomes prohibitive at no extra advantage. Okay. So let's say for a structure, let's say it's just say a 3-bedroom house. It is not economical to have it, to model it with multiple columns of, say, 500 millimeters by 500 millimeters. Yes, the structure is going to be safe. It is not going to, say, fail under the loads you anticipate it to face in its design life. But when you look at it in an economical sense of view, it is going to be over-designed. The factors of safety that you are providing for that structure are going to be so generous that the construction phase may be, the construction price may be prohibitive. And we know we exist in a world or in a reality where resources are scarce. So for a client to come to you, they come to you with a budget, and you try as much as possible to fit within that budget, but you do not undercut the safety. So that is it. You just have to balance uh, the the safety of the structure as well as the economical aspect of the structure. Please ensure you are muted. Please ensure you are muted. Okay, so we have that. Then from here, I'd like to go into the design procedure of how personally I approach design. This is not cast on stone. You don't have to approach it in the same, in the same manner. And it would change or it would alter from project to project. And if you say have any additions to any steps here, I'd like to see that in the chat box so that we can all learn from each other. So if there's something that you would want to add from this or remove from this, we would love to see it in the chat box. So this is how I approach structural design. So the first thing is the initial consultation with the project, all right, or with the client. So we have an initial consultation and project brief. So in the initial consultation and project brief, here is where you get to understand the project itself. Okay, so remember, when structures are coming up or when projects are coming up, you are not working together. You are working with other professionals, such as the architects, the quantity surveyors, geotechnical engineers, and others. So you are not working alone. So for you to get to understand the project, you have to be in communication with them. You have to get more information from them. So in this initial stage, I always tell, say, our participants, in this initial stage, it's for you to listen, okay? It's for you to listen, get to understand how they intend to use the structure, okay? You might go to, say, a consultation with the client with your beliefs or how you approach your design. So you are used to having buildings uh, with with walls, say with walls where you with permanent walls, okay, or with you are used to buildings that have been, say, permanently partitioned. That is from the architectural drawing, you know where your masonry walls are going to be placed, but probably from the initial consultation with a client, you get to understand that they do not want any partitions. They want just an open space. Probably they want to use that space for a gym. Probably they want to use it for a church, or they just want to create an open space where their tenants can come and, say, rent on an uh, on an area on an area space type of contract. I think those types of contracts are common in the business districts, where you have, say, a tenant come and tell you they need 75 meters squared, and then from that you partition it for them. So for such a case, you need to understand, or you can only understand it by listening to the client, getting to understand what they want to use their structure for. All right. Then after you understand what the structure is to be used for, then you can do your site investigation and data collection. So with site investigation, it involves going to site, getting to understand how, say, the soil is, how the boundary conditions are, the type of environment it is in, so that you can use that data in your design. So at this point, you may be able to collect data or information on the bearing capacity of the soil, say the wind speeds of that area, and say when it comes to the boundary conditions, it gets to influence even how you model and how you design your foundations. Say you are working on a structure that is going to be built, say, near the boundary of the of the plot or of the land. You may not want to use concentric footings. You may go for eccentric footings so that you move them towards the inside of the plot, so that you're not going to someone else's plot, right? So uh, I hope you understand now from the first two stages, you are majorly gathering information. You are gathering the constraints that will control how you approach your design and your analysis. Then after you have enough information, you can go to the preliminary structural design and member sizing. You can call this the conceptual stage of design. And this is where you're majorly making educated guesses, and you're, say, idealizing how the structure or how the frame will be. So you're going to be looking at the spans and saying that for this span, I would want to start my design with a beam of 200 by 450 millimeters. For this structure, I would want to use small columns, say 300 by 300 millimeters, etc. So that is what you do in the preliminary structural design and member sizing. Then after you do your preliminary structural member sizing, you now get to load that structure that you have idealized. And then after you load it and create the necessary load combinations, you get to analyze that structure and go through the design phase or the detailed design. So in the detailed design, this is where you get to incorporate the results from your analysis. You get to look at each member individually, get to look at a column, look at the actual loads it is facing. Is it, say, a short column or a slender column? You take account of that in this step. And then it's from this step that you get the results that are going to be used in the construction phase. Okay, and then now from there, you go to the structural review and compliance checks. So this one is going to be majorly done by someone who has more experience by you, or someone who you are working someone you're working with. So they're just going to go through your work, see if you made any mistakes or if there is something that you should improve on. And then after your work has been reviewed, you're going to go through the coordination with other disciplines, especially now that we are kind of moving into a BIM-oriented workflow. So you get to coordinate with the architects, with the MEP engineers, with the landscape architects, and ensure that everything that is involved, all the members of the structure, they are well coordinated. There won't be any conflicts once the construction has started, right? And then once everything is in line, you can now move to building, acquiring the building permits from the appropriate authorities and getting the approvals. And then from there, when you have everything, you can move to tendering and construction, right? So we have that. So we have the design procedure on our hands. So we can now move to design considerations. And what you're going to notice in the design considerations that I have listed is they will majorly come from the first two stages of the procedure. So the design considerations are basically what you're going to understand from the briefing with your architect, with the client, and also from the data and the investigation you did. Okay, so some of the things that you may want to consider are the structural use and function of the structure, the environmental conditions, the expected durability and fire safety, constructability and maintenance, and economic and, say, sustainability factors. So you can see that, say, from the structural use and function, they are going to affect aspects such as loading your structures. Say if a structure is to be categorized as a residential building, it is going to have different loads from something that would be categorized as a commercial building. Okay, then the environmental conditions would affect, say, the cover conditions for your members, and also the loads that you're going to be using for simulating your winds, and also if it is in an area that is considered seismic. Those are some of the things that you'd have to consider at this point. Then the expected durability and fire safety. Different buildings will have different expected durability and fire safety features. So if you're doing a structure like a hospital, a school, they're going to have a higher expected durability in matters fire safety. But if you are doing, say, the normal residential buildings, they may have a smaller, say, expected durability that could be even 45 minutes or an hour. So those are some of the things that you have to consider. And then once you have these design considerations, you can move to design itself. But as we approach design, we have to consider that there is always going to be uncertainties when it comes to design. We may, sorry, we may want to, as engineers, we may want to be as perfect as we can. We may want to, say, simulate our loads as perfectly as you can, but most of the time it is impossible to do that. And this is why we have to consider the uncertainties that are involved in structural analysis and design. So these uncertainties may arise due to load variations, load distribution, analysis simplification, structural behavior, and construction errors majorly. So when we are talking about things like load variations, we are saying, or we are suggesting that you may consider the typical, say, live loads that you expect certain structures to be exposed to. So if you, say, are designing a residential building and you consider, say, a live load of around 2 kilonewtons per meter squared, you'd be well within range. But sometimes you may find your structure exceeding those expected loads. I think those who are, say, close to the East African community, there was that tank there was a picture going around of a tank, a steel tank, that had a lot of people, say, scale it to be able to see, or to see the proceedings during the burial of the late, late Raila Odinga. I hope you can remember that tank or that stand. We are sure that no one had anticipated that tank would be exposed to such magnitudes. Okay, but during the analysis and design, probably the method that was used to design had some way of accounting for such an occurrence, and that's why it was able to safely withstand those loads. Okay, then we have load distribution. We cannot perfectly, simulate how loads are going to be distributed in a structure. We may say that, say our slab is two-way. We expect that from this slab, this amount of load will go to this beam, this amount will go to this other beam. But saying that you're going to be 100% say perfect with that load distribution, I think it's going to be an overstretch, and it is kind of impossible to simulate that. Right? Then we have the analysis simplifications. Whether you are using the software or whether you are doing this manually, we are always going to try and say simplify the calculations into something that we can follow and something that you can do. Say, for example, if you are doing your loads, say manually, if it's a slab, you assume either it's a two-way or it's a one-way. All right. And then from there, you're going to try and find the areas of the slab that are going to be distributing loads to certain members. And then from those certain members, they distribute columns and finally to the ground. So when we are simplifying this analysis, we have to account for the scenarios where our analysis is not perfect. Okay, we have to account for the we have to account for the we have to account for the scenarios where our analysis is not going to be perfect, and just ensure our structures are safe for that. Then the other thing that is important at this point is structural behavior and material strength. Okay, I will put these 2 points together, the structural behavior and the material strength. For those of us, I know I've seen this comment a lot. It's probably something that is quite common, say, in the African continent, where you have, even the suppliers undercutting you on the materials that you are buying. Okay, you can buy, say, a steel bar. It has been rated as a 16 millimeter bar, but in reality, it could be 15 millimeters, or it could be even as low as 14 millimeters in diameter. And for the strength of steel, or the amount of stress that it can withstand, it is usually rated in newtons per millimeter squared. So the smaller the diameter is, the less the stress that it can withstand. So if the bar has been reduced significantly, then you're going to get, say, a smaller strength or less strength than you had, say, appropriated, or you had assumed during your design phase. So you are not in control of that. That is not something that you can always depict and say that I'm going to get this accurately. So you need to account for that during the design phase. All right. And then we have the construction errors. So sometimes it is construction errors are always going to be there. We are humans, and these structures are going to be built for humans by humans. So we expect some errors to occur. All right. Sometimes you may even detail your work correctly, but when you go to site, you'll find that some people have done their own things. And then you have to try and account for that during the design phase. Something even as small, say, as ensuring your columns are plumb, they are, say, perpendicular from the ground up. Sometimes that does not happen. Sometimes even if you look, say, at existing structures, you're going to notice that some columns look like they're leaning outwards, or some are leaning to the side, and some are leaning inside. But the structure is still safe. Okay, the structure may not be that aesthetic, but For some, for the layman, they may not notice that. But for you, say with someone with say an engineering background, will be able to say that this column here is not that plump, and there must be something that went wrong during the design phase. All right. So that is what those are some of the uncertainties in design. And when we have these uncertainties, we have to account for them. So the issue comes to how we account for them. And how we account for them is using the design philosophies. Okay, so we have various design philosophies, and the design philosophies include the limit state method, load factor method, and the modular ratio method. So before we go to the methods themselves, let's again just talk about the design philosophies. So as the designers, you are number one. You need to ensure that your structures remain safe under the most extreme loading. You also need to maintain acceptable performance under normal operating loads with deformations that do not affect the appearance, durability, or functionality of the structure. You do not want anyone to feel unsafe in your structure. So that's why we have to maintain an acceptable performance under normal operating loads. And then number three, we have the cost effectiveness, or just ensuring our designs are cost effective. So as we approach design, we have to take care of these three. We have to have these three at the back of our minds. And then we are going to approach the design methods. And then these design methods are majorly tied to the uncertainties in structural analysis and design. So we have the permissible stress method, and it is also called the modular or elastic method. And in this one, how these design methods or the design philosophies, they are basically say a set of they're basically fundamental sets of principles, assumptions, and approaches that guide the planning, analyzing, and design of structures. And they are there to ensure that our structures are safe and durable. All right. So basically, they are just principles, assumptions, and approaches that guide the analysis and design of structures. And they are majorly tied to the uncertainties that we are likely to face during the design and construction of our structures. So there are these three main approaches that we have. We have the permissible stress method, the load factor method, and the limit state method. In the permissible stress method, that is also probably often referred to as the modular method or the elastic method. In this one, to cater for the, say, uncertainties, stresses acting on a structure are not allowed to exceed a certain proportion of the yield stress. Okay, so to explain what the yield stress is, the yield stress is basically the point or the stress at which a material stops to behave in an elastic behavior. That is, an increase in strain stops to cause an increase in the stress in the material. Right. So we have the permissible stress, and how this accounts for the uncertainty is so the loads are the ones that are going to be causing stress on your structure. So to ensure that they do not exceed a certain proportion, you divide the loads, you divide the material strengths of the construction materials, their given factor of safety, and then ensure that the loads that you're going to have on your structure do not exceed that particular stress. All right. This method was majorly used in the older codes, such as the CP 114 and BS 449. But at this point, I think it's not commonly used. And then we have the load factor method. The load factor method it's majorly more plastic, which considers the construction materials in a more plastic nature. Okay. So in a plastic nature, we are saying that once you approach the yield point, it assumes that the materials will not fail immediately, but rather they are going to take more load. And then after that load, they will not be able to, they will be deformed permanently. Okay. So, so what you are saying here is for the load factor majorly, just to simplify it, you're going to be multiplying the loads by a given factor of safety, just to create that factor of safety so that you're like over designing for it. Okay. The load factor of safety is majorly used for steelworks. It was majorly used for steelworks, but it was not, say, its uptake was not that high, and it was overtaken by the limit state method. So the limit state method is a more robust, say, method of approaching design. It considers both the material weaknesses that may arise and also the loading factors. So in the limit state method, what usually happens, just to simplify it, is that you divide the material strengths by a given partial factor of safety, and you also multiply the loads by a given factor of safety. I'm sure if you've, say, been exposed to the Eurocodes, you've come across factors of safety such as 1.15 for steel and then, say, 1.5 for concrete. So you divide the yield stress of those materials by those factors of safety so that you can get the stress that you're going to use in your design. And then when it comes to loads, I think this one is the one that we are, say, we are more, say, adept with. We've all, say, seen the 1.4 GK plus 1.6 QK for British standards, and then we've also seen 1.35 GK plus 1.5 GK for the Eurocode. So those are the factors that are used to amplify the loads that your structure is likely to be exposed to in its say in its design life, so that you always have that factor of safety during design. Okay, so I don't want to bore you with a lot of theory. I want now to move to a more practical sense. But at least now we have some background, and we can now approach the design. So I will just go to the project information and what you are going to be doing, what is the scope for this particular sprint. So we are going to start with interpreting the architectural drawings, and this one is going to cover what we had in the first stage of our design process. So at this point, we are going to be more concerned with getting to understand the architectural project and how it is going to influence say how we place or where we place our structural elements. So what I'm going to do is I'm going to open up the architectural file on my end. And then once I open it up, I just like to, I hope you can see it. If you can make out anything from my screen at this point, please type a one. If you can see the architectural file and make out the dimensions, probably how the space has been utilized, please type a one. Super. So I can see we can see it clearly. So before I proceed, so at this point, we want to do our preliminary, say, sizing and get to understand how we are going to approach our design. So I just want a few volunteers, probably 2 or 3. Let me get to hear what you understand, and then from what we have here, how we should approach, say, our column modeling and placing our beams. Okay, so just take it up. Anyone, whoever goes first, just to save on time. Feel free to share with us. We want to hear from you. What can you see on the screen, and what do you think we should do, especially with regards to modeling our columns and placing our beams? Also consider this is a three-story structure, so just have that in consideration. Let me get to hear what your thoughts are. Anyone willing to go or give it a trial? Boss, please take it over. Please go.
Right. Thank you so much for guiding us through this. I think at this point, you want to look at the building in terms of what is the arrangement of the rooms that the architect has given you. You
Yeah.
look at the ground floor, and then you look at the first floor, depending on how many floors are coming on top, and then you see if you put, if you say you are going to put a column from down, does it go through, maybe can it be linear to the last floor up? Or at some point it's going to like end somewhere, and also the arrangement of the columns and beams, is there going to be a column somewhere randomly placed in the middle of a certain bedroom? So you want to first, for me, where I would start from is to look at the entire drawing so that I get context on where I can place columns in a way that makes it efficient for the user of the building. Thank you.
So I think you brought something really important and something that would affect, especially when you're designing the mansionettes. They're usually difficult to place columns because the use of space is not standard. You have rooms, say, changing from floor to floor, and it becomes a bit difficult to place a structural element. So that is something that you'd have to consider at this stage. Someone else, one more person, and then I'll proceed. One more person.
Okay, good evening.
Good evening, Bright.
Yes, am I audible?
Yes, you are.
Okay, so for me, the way how I usually approach this, the first thing that I do is I clean my drawing using AutoCAD. So I will take the ground floor, then take the first floor, and then the second floor. So you superimpose the first floor on top of the ground floor, and then you superimpose the second floor on top of the first floor, and then if there is a third floor or a eaves layout, then you superimpose it on the second floor layout. So from there, I will just take I can say my walls.
Yes.
You clean out the walls and then you leave the openings. So what it means is when I'm now modeling, I'll be looking at where I've got openings. That's where I'll be putting my beams, and then maybe checking the spacings. I then align my columns depending on the spacings that I'll be having. That's how I usually approach it.
Super. Thank you.
All right,
Right.
thank you.
That's how you're going to approach it. But just in the interest of time, you're just going to use one floor to place our columns and our beams. So we are going to get started. So when you have, say, an architectural file and you want to just understand where you may want to place your beams, the first thing that you may want to look at are where your major walls are. So you may want to avoid, say, loading whenever possible. You may want to avoid loading your beams or your slabs directly with the heavier walls because they are going to make them a bit deeper and require more reinforcement, which would in turn make your project a bit more expensive. So whenever possible, sometimes it's not possible, but whenever possible, you would want to load the wall loads directly on the beams. So what I'm trying to mean is that where you have your main walls are some of the points where you can choose to place your beams. Okay, not all walls may necessitate you to have beams. So for example, the partition walls and the smaller walls, you may choose to load your slabs directly on those points. But for the major walls, I'd always recommend you try and have beams whenever possible. Then the other one is placing your columns. So majorly for columns, we're just going to be placing them at areas where we think our main beams are going to be intersecting. And we would also want to limit, say, our beams to say to spans of around 8 meters to 10 meters. We don't want them to be very long because we say we need them to pass the deflection checks. And they're also going to be a bit more expensive to design for if they are very long. So if they are very long, whenever possible, just try to limit them to say the 6 meter, 8 meter range there, and you're going to get some good designs from there. All right. It also reduces the risks that would say come with design very long members. All right. So we have that. We want to design this member. But before I talk about placing the columns, I will now go to the software. All right. I will now go to the software, and this is the software that we are working with. So once you open up Robot, this is how it looks like. Okay. This is how Robot looks like. So once you open up Robot, this is the landing page. So on the left, you have the new project, and under new project, these are basically the templates you can work with. Okay, these are basically the templates you can work with. So with Robot, you can create multiple projects. So you have your first template being the building design. This is where you do your 3D modeling and design for buildings. You can use this for both RC and steel. Then we have the second template. This one is majorly for load takedown and building design. So here, if you don't want to do, say, your design, you just want to have a load takedown, get to know how the amount of loads that are going to be transferred to certain members, and then design them manually or using Excel sheets, you can use this and combine the two tools. Okay. Then you have frame 3D design. So this one is just for the design of 3D elements of frame of steel structures, basically steel frames. All right. Then we have the shell design. This is basically for the design of shell elements and structures such as silos. So if you are in an environment that deals with silo design majorly, you may be interested in this template here. And then we have truss 3D design. So here you just design your trusses in 3D. Then we have these other types of structures or templates. So you can use this one to design your slabs. So you don't want to model slabs for the entire structure. You're just interested in designing the slab that you consider the most critical one. You can use the slab design template here. And then you have the frame 2D design. And in the frame 2D design, you just design one frame. Say if you're working, say, on a frame structure, say a go down, it has a couple of trusses and columns supporting those trusses. So if you don't want to design for all of them and you are only interested in designing for the most critical, the most critical part of the frame, and then use those results for the other frames, you can use this method here. Then we have the grillage design, and the grillage design is majorly used for the hollow pots and the waffle slabs. So you can use this template for that. Then we have truss 2D. So this one you just use it for 2D design of your trusses. Then we have the volumetric structure design, and this one is used majorly in the design of structures such as dams and structures such as weirs. Then we have the plane stress structure design, and this one is majorly used for the design of walls and wall-like structures. Then the other most common ones are the RC element design and the connection design. So the RC element design is used when you want to design one element at a time. So for those, I had a few of us are say have experience with Procon. So the RC element design template works in a way that is similar to how Procon works. So if you are designing just a single beam or one continuous beam, if you are designing one column, if you are designing one footing, you don't want to design the entire or have the entire 3D model, you can use the RC element design. So if you like how Procon works, or if that is what you are used to, I'm sure this RC element design, just this element design would surface for you. Then we have the connection design, and this one is for the design of steel structures. So after you've done your analysis and you want to design your connections, you use this template here. So for now, we are going to be focusing on coming up with a 3D model of an RC structure. So to do that, I'm just going to click on New. Then I'm going to go with the first template. You're going to find that this is the template you're going to be majorly using. So I just click on New, then select the Building Design template. Then once it opens up, this is how the user interface looks like. The user interface with robot, it's very simple. It doesn't have a lot going on. You can see I do not have, say, a lot of tools to go with, and you're going to realize that everything is, say, quite accessible. All right. So this is how the user interface looks like. At the very top, I hope you can follow my cursor. At the very top, you can see the version of robot you are using, the name of the project. So I'm meant to name it, and it has gone with the default name, that is project structure. And then on the right, after the name of the project, you can see the status of your analysis. Once you do your analysis, the status of your analysis is going to be available. But if you are ready to do your analysis, the analysis is going to be none. And then on the right, you can see the email I've signed into the software with. And then you also have access to the Autodesk Store and Autodesk Help. Then after that, we have the ribbon. And basically, the ribbon is the collection of the tools that you're going to be using to model your structures. When taking, say, our participants through working with a ribbon, I always recommend don't try and cram where the tools are. Don't try and cram where things are. Just try and understand how the how the software has been organized. And then as you work more with the software, you're going to just know where they are. It becomes so easy. You don't even have to think about where the tools are. Okay. So just don't focus on cramming where the tools are. Just try and understand how the user interface has been arranged. So to the left, we have file. This is basically file where you open a new project, where you save, etc. So this is where you have file. And then we have edit, and edit does what edit essentially means. We have undo, redo. If you want to make changes to something that you've modeled, you do it in the edit tab. Then we have the view, and the views, they basically majorly affect how you view your elements. Okay, so when you are working with robots, it's quite sensitive when you're studying. So if you look at my screen, you can see a few dots. If you can see the dots, please type a one. So when you're working with robot, it's always going to try and snap with these dots. And if you're not aware of that, it is going to bring on a lot of errors down the line. Okay, you're going to be modeling your structure, and once you get to the analysis phase, you are going to find that some of your panels are overlapping, or some of the columns were not, some of the beams were not snapped to the nodes that you intended them to snap to. So whenever you open up a project in Robot, I always recommend go to View and then click on Grid here. And then once you click on Grid, you're going to once you place your cursor here, just scroll to turn off grid and then turn them off. So once you do that, you're going to be now in control of where the software snaps to. And it's going to help you be more accurate with your modeling. Then now from view, we go to geometry. And in geometry, this is the tab that we're going to be using to come up with our structure. So in the geometry, we can define the structure type. Okay, So we can still access the templates from here. If we want to change, you can do it from here. So I'm going to stick with what we had earlier. I'm not going to change it. So I'm going to stick with the 3D modeling. And then after 3D modeling, you can do your axis definition. Okay. And those who are new to what axes are, so axes are majorly just a coordinate system. I'd consider them a planar coordinate system, and they assist you in locating your structural members and also communicating where they are. And then when working with the software, it is always easier to model where a grid is. Okay. So when you're working with the software, even if you don't want to have a grid say on your detailing, I always recommend you rather have the grid there, model with it there. And then when it comes to the documentation bit of the design process, you can delete it. Okay, so we have that. Then from there, from the geometry, basically this is where we access the tools to model our structure. All right, and then all these tools are accessible via the modeling tab on the right. Okay, all these tools are accessible via the modeling bar on the right. You can see where I'm hovering with my cursor. So you can see, say, at the top, we have axis definition. And then the very first tool I have here is axis definition. This is what enables us to draw the axis. And then we have stories. So to define our stories, say the story height, etc., we define it here. So you can use these tools here, or you can access it from here as well. And then you have your nodes. Nodes are automatically created. And Robot will always create a node where you start your element and where you end it. Then you have members, and members in Robot are basically your columns and your basically what you'd consider to be part of the frame. And then you have your panels, and panels are basically your floors and your floors, your cladding, your roofing, and also your shear walls. They fall under panels. All right. And then you can see more of these members exploded here, but no worries, you're going to explore them as we go. Then after geometry, we have loads. This is where you define the types of loads that your structure is going to be, say, exposed to. Then you have analysis, and then you have results, and then you have design. Okay, so look at how the software has been arranged. It's very simple. So you start with setting the view, okay, what we did. Then after you set the view, they expect you to start modeling. So the tools that you used for modeling or you are going to use for modeling are located here, and you can still access them from the right. All right. Then after you have your modeling tools, they expect you to define your load types and your combinations. So after you've defined your geometry, you define your loads and your combinations. All right. So the software is arranged in a manner that guides you. Okay. So after your loads, you're expected to do your analysis. So you define the type of analysis you want, and then the software is going to do the analysis for you. Then after the analysis, we expect you to go through the results, get to make sense of them. Okay. And then after you've done after you've read your results, then you can proceed to design. Okay. So you can see from how it's arranged, it's more of even guiding you on the steps that you're supposed to take. So set up the view, do your modeling, define your loads, do your analysis, do your results, then do your design. And then here you just have more tools. And these tools are what we use to make our modeling a bit easier. So this is what I always recommend when you're working with the software. The first thing that you have to do is go to grid and turn off grid. Ensure those dots are not visible. Then after you do that, go to tools. And then after tools, after you click on tools, you go to job preferences. And it is under job preferences that we get to set the type of code that we want to use. So the software has been built for many people, and it has been built for engineers all around the globe. So it has different databases that it can refer to. So it has the ACI code, it has the British Standard codes, it has the Euro code, it has most of the codes that you would need. So for us, we have to set it for the environment that we are in. So for me, I'm in an environment that is currently using the Eurocode. So to set that, just to repeat, you go to Tools, then you go to Job Preferences. Then once you go to Job Preferences, you can make more settings here. So for example, I will start with expanding units. And then once I expand units, I click on Dimensions. Then under dimensions, you can define how you want your, say, the dimensions to look like. So under structure dimensions, I can define the distance between my grids to be left as meters. So you can look at what your architect has. If his units are in millimeters, you can change yours to millimeters. But when using robot, I just prefer to have mine as meters. Then you have the section dimensions. So in the section dimensions, these are the dimensions of the cross sections. Are your members, say, 200 millimeters by 500 millimeters? Is your beam depth for 50 millimeters? That is what the section dimension is. So if you want to have that as centimeters, say have a beam that is 20 centimeters rather than 200 millimeters, you can change this to millimeters or to centimeters. For the section dimensions, I prefer to have millimeters. I think that's what I've just grown used to. And then you can look at the other dimensions. You can see the dimensions of the RC bars. They're in millimeters. Reinforcement areas are in centimeters squared. And crack widths are the same. Then you can go to forces. You can see everything is in kilonewtons and kilonewton meters. So I'm just good with that. Then unit definition. So you have the unit definitions here. So under other, I always like to change my displacement to millimeters. So because the displacements I expect are usually very small figures, so millimeters would make more sense for them. Then for databases, I'll just go over this quickly. You can see the databases that are being referred to, and these ones are going to be controlled by the design code you select. So when I go to design code, this one is the most important for me. I'll always ensure that my design codes are Eurocode or Eurocode based. Sometimes you may want to change to certain Eurocode annexes so that you can design for elements such as shear walls. But for now, since our structure does not have any type of walls, I'm just going to go with the basic Eurocodes. If you want to change them, you just click on the drop down, then you can click on more and select the type of code you need, and then set it as current. But for now, the Eurocode is just sufficient. Okay, so I think we've had enough with that. So we can start to do the modeling. So to start the modeling, it's going to be really easy. Before I do that, let me confirm my story heights. So I'll go to structure stories and ensure that my story height is what I intend to have. Okay, always do this before you model, because you may not. It may be a bit troublesome to change the story height once you do. So you can see the project I had opened up. I was working on a tank, so it had a story height of 4.4 meters. So I need to change back to what I expect for a residential project. So I'm going to be working with a story height of 3 meters. So I'm going to change this back to 3 meters. And to do that, it's really easy. I'll just select this story and delete it. Then go to define manually and change the height to 3 meters. All I need to do is type 3 meters and add it. Then once I have that, just apply. This one is important because when I place my columns, they are going to follow this height. So if I had modeled them with the 4.4 meters, they would be placed at or with heights of 4.4 meters. Okay, so once I click on apply and close, I'm going to have this. Then I'm just going to scroll and ensure I'm in story 1. All right, then once I'm here, now we can start creating our grids. And when creating our grids, we may want to follow what the architect has, okay? We may want to follow what the architect has, try to model the grids as he has modeled. But the reality is sometimes you may need additional grids that he did not have. So here you're a bit lucky. Probably the structure is quite simple and you have grids at almost every element. But in some instances, you're going to find yourself working projects that you have to introduce new grids. So we're going to create a few grids here, and it's really easy to do. So to create grids in Robot, this is what you do. You just go to your modeling bar on the right. You can click on the axis definition or access it by going to geometry. So you can access it in either way. Using the modeling bar is easier. So I always recommend go with what is easy. So select axis definition from here and define your axis. So we have three axes. We have the X, Y, and Z. So if you look at my screen, you have the axis, the global axis here. So you have Y in this direction and X in this direction. You can see Y is pointing upwards and then X is pointing towards the right. So this is telling you that X in Robot is from left to right, and then Y is from bottom to top. So when you want to define your axes that are the axes that are spaced along the X direction, just ensure you're in the X direction. And then you're going to start with creating the first axis. So I'm just going to have my distance 0, and then number of repeats 1, and then I. And I'm going to have an axis at the position 0, 0. So the position 0, 0 for me is here. So this is where my grid 1 is. Then to place my grid 2, I will enter the distance between grid 1 and grid 2. So at this point, I know the distance between the two grids is 0.58 meters. So what I will do is I will just come here, I have the number of repeats as 1, and then enter the distance. So my distance here is in meters. You need to be careful with that. If your distance is in meters, always ensure it is in meters. Otherwise, you may end up modeling a structure that is more than 1,000, meters long, and it's going to give you trouble. You're going to find your members failing, and you don't know why they are failing. It's because you are designing, say, beams that are 580 meters long, which do not make sense. So always ensure you follow or you convert your measurements correctly. So I will have my grid 2 at 0.58 meters from grid 1. Then after that, I'll proceed to create my second grid, 4.02 meters. So I just go to the software, in the distance type 4.02 and add it. Then from there, I'll go to the next grid, that is 3.4 meters. So I'll just type 3.4 meters here, then add it. Then from there, I have a second grid that is, say, 2.365. So I'll just type that, 2.365, and add it. Then after that, I will go again. So I'm just reading the distance and then typing them. So I have 3.4 again. So I just type 3.4 and add it. Then after 3.4, I'm going to have 4.02. So I add 4.02, add it, and then finally 0.58, and then add it. So I have my grids. Then once I'm done in the X direction, this is the X direction and this is the Y. So once I'm done, I'm going to go to my Y direction and paste them. So my 0 is always going to be at the bottom left. You can see where my 0, 0 is. So here's my 0. My 0 is at the bottom left. So I'm going to have these as distance 0 and number of repeats as 1. Then add it. So that is the position of my first grid. Then I will start from the bottom. So I will start from the bottom going upwards. So my first grid is 0.87 meters. So I will have my distance here, 0.87 meters, and then click on add. Then from there, I'm going to go to 3.52. So I'm going to add my distance here, 3.52, and add. Then from there, I'm going to grid the next grid, 1.42, twice. So I'm going to click to add 1.42 and add it twice, 1, 2. Then I'm going to add the second one, 2.19, 2.19, then 0.98, then add it, then apply. And then once you apply, you have your grids. So something I forgot to mention is that you can change how your grids are numbered. So at the moment, you can see all my grids are in numerical figures. You can see the grids along Y are numbered 1 to 7, and the grids are now say numbered left to right are also in numericals. This is an ideal. You essentially want to have one set of grids numbered or ordered alphabetically. So I'll change the ones along Y to the alphabetical order just to match this. So I will have this change the numbering at the bottom where you have numbering. You can use ABC, enter values, or define them manually. So I'll just go with ABC. It's easy. You can apply and close. And then I have my grid step. So this is what we'll do. We will model columns, and I'll just start with them. I will start on the bottom left. And for this structure, I'm just going to start with an assumption of, say, a 200 by 450 millimeter column for this structure. And then probably for the interior ones, I will do 200 by 500. So what I'm going to do at this point is this. I'm just going to explain how I approach orienting the columns. I think it's something that is really important to grasp before you even start placing them. So whenever possible, sometimes it's not possible, but whenever possible, try and do this. If this is the panel, say if this is the panels that you have designed for, say you have a slab, or you have 4 sets of beams. You have beams that are longer than the others. Okay, you have beams that are longer than the others. All right, so you have beams that are longer than the others. So when you have beams that are longer than the others, you expect loads that are coming from the longer beams to be more than the loads that are coming from the other side. So when you have your columns, let me change a color to yellow. So when you have your columns here, assume this is a column, it has 2 axes. So you have the axis along the longer side, so axis along the deeper side, and axis along the shorter side. So this is going to be our major axis, and this is going to be our minor axis. So you expect that this collar will be able to resist more bending along this direction. So whenever you are, say, doing your preliminary modeling or your conceptual, say you're in your conceptual stage, the stage you're in, always try to have the longer side be in the same line or be parallel to the longer side, so that because it can ideally resist more bending in this direction. So what this does is it makes your design a bit more efficient, and you're going to end up requiring less reinforcement in this direction. All right. Then this one can also be influenced by how the panels have been arranged. Say you are designing for say such a point. You have a point here, right? So you have a beam on the left, a beam on the right, and then in this direction, you have no other beam here. So you may expect that these 2 beams here may behave in some way like a seesaw. So the moments on this beam and this beam, if there's a support here, they are going to kind of counteract each other. So you expect, say, minimal net bending in this direction. So for this case here, you may prefer to just model your beam with a longer side in this direction. But again, this one is not cast on stone. It depends on the scenarios you find yourself in. Okay. Say, for example, if there's a door here and there's a window here, you may not be free to model it in this manner here. You are constrained by the, say, architectural needs and the the usage of the structure. So in that scenario, you may be forced to design it in this case, right? Not that this is wrong, just that this method is a bit more efficient and more economical in the design phase. Okay, so what we are doing here is just the conceptual design phase. We are making, say, educated guesses on the sizes of the columns and members we need. And then from there, tomorrow, we are going to do the design and get the actual sizes we need. So at this point, we are just doing the preliminary sizing. Okay, just making an educated guess of what we need. So we will start with the columns. It's going to be really easy modeling them. So to model columns, you're going to go to the modeling bar here, and then you're going to select the columns here. So this is the option you select for modeling columns. So you're going to left click on the columns. And then once you do this, you have this pop-up appear. The first thing you need to do is select the type of column you want. So you can do timber columns, RC columns, or steel columns. We are doing an RC structure, so I'll go with RC column. Then click on these three dots to define the type of section you need. So give it a label or the name. I'm going to call it column 1, 200 by 450 millimeters. Then in the width, 200, and in the height or the depth of the column, 450 millimeters. Then I will click on add and close. Then once I do that, I will just place my columns. So in this panel here, I probably expect, what's the distance here? I expect this is the longer side. So I'll just orient it. I'll just orient it in this direction here. So let me look at where this is. This is a second grid. I will place it here. So once I place it here, you're going to notice that my column has not been oriented in the direction I had wished for, or I wish to direct it. So to change the orientation of a column, you just select it, and then in the options on the bottom left, you can change its orientation. So to change its orientation, you just go to Properties, Expand Gamma, and you type the degree of rotation, and then you just click somewhere, and it's going to be oriented. And that's how you model it. All right. And then once you're done with the first column, you can copy it or model the others. So I'll quickly model the others. So for these ones, I will orient them in this direction. So I'll place another one here and another one at grade C. So it's really easy. You just go to column modeling, then you place it. You place the first one here and the second one here. Then I'll do the same thing here and here because they are modeled in the same way. And then just to save on time, I will copy this one. And to copy in Robot, you just go to this option here, Edit, or you can go to Edit here and select Copy. So to copy in Robot, just highlight the item you want to copy, then go to Edit and click on Copy. Let me go to copy here. So this pop-up appears and then I can copy it. So all I need to do is left click on the center of the column and copy it to these other points that I need to place it at. So it's here and it's here. Okay, so if you look at my structure, there is some form of symmetry. So that's why it's easy to copy the columns to the other ends. All right, so I'll proceed to place the other ones. So at grid A, let me see, I'll place a column at grid G here and at grid here. So at grid 3, so let me do that. I'll just place a few columns. I will copy this one. Again, to copy this is how you do it. You select the column, then you go to edit here. It looks like a square rule, so you just click on it. Then you click on the second option, move stroke copy. Then all you need to do is left click on the center and then place it at the points you want to copy it to. Okay, and this will be a bit easy for us to do. And then you can close that once you're done. Then to copy them to the other end, it will follow, the basic principle. You could just copy them. So to make it easy, also to demonstrate how you can easily copy, I will just highlight them. And to highlight them, I'm just left clicking, holding my left cursor. And then once they are highlighted, I'm going to click on move stroke copy. and copy them from this end to this other and there, and close. And now I have at least some of the, most of the columns that I need. Then from here, I will proceed to model the others. So here you can look at what I was saying. So you may want to orient your columns in this direction because these beams may seem to counter, to counter each other. But the reality is you may not want to have them go into the kitchen or in this space here. So you may just choose to align them along the wall, and then you'll just end up with members that you can easily hide within the architectural components. So for these columns, I will just orient them in this direction here. All right. So I'll place a column along grid E and along grid C. So that is at this point and at this point. So I'll just select this column here, go to move stroke copy, and copy them from this center here, click here, then from here to here. And then to make this simple, I'll just highlight them, okay? And then copy them. So I will copy them from here to here, and then from here to here. So I'm just following the architectural file and placing columns where I deem necessary. And for me, I'm basically placing them at the grid intersections of my major beams. And with that, I have the major columns that I need. So this is what I usually do. I usually model my columns using one, whenever possible, I model them using one cross section. And then, say for the interior columns, you may say you expect them to have more loading or more axial, axial loading. So in the design, you may end up needing more reinforcement or even having to increase the cross-section size. But at this point, since you are just doing conceptual, say, modeling or conceptual design, these are just, say, educated guesses of the required, say, of the required sizes. So we are just going to model them as they are. And then tomorrow, as we design them, we are going to come up with the required or the actual sizes that we need. All right. So I will proceed to model the beams for this floor, and it's going to be really easy. So to model beams, you go with the beams option over here. So I'm going to click on beams right here. Okay. And then once I click on beam, just as we did for the columns, you select the type of material that you need. So at this point, I'm only doing RC beams. So I'm going to select an RC beam. Then after you select an RC beam, you're going to define the section. So I'm going to click on this drop down and define a section. So I'm going to work with 450 millimeter beam because I think that's the minimum, dimension you can work with, at least for these types of projects. I'm going to work with a 200 by 450 millimeter deep beam. And then if during the analysis and the design phase we get to need a larger beam, we are going to do that. But for now, I will work with 200 by 450 just as a preliminary size. So I'll just add it and close. And then once I do that, I'm going to start modeling. So when it comes to beams, it is important to understand that we have majorly two types of beams. We have secondary beams and we have primary beams. So primary beams are beams that are directly connected to the columns. They transfer the loads to the columns directly. And then for the secondary beams, they transfer the loading to other beams or to say a beam and a column. So when modeling, I always recommend you start with your primary beams and then you proceed to model your secondary beams. So I'm going to start with my primary beams and I'm going to model beams that are connecting to my columns. So if you look at our file here, we have these major walls. So I'm going to start connecting these columns. So I'll just go to the software and then I will check drag so that I can drag from one element to another and then just place my first beams. All right, so I just proceed to place them. It is relatively easy to do. And with that, you have the beams that you need. Okay. And then after you've modeled, say, the first set of beams, you can make your work easier. You can copy the beams that are similar. So you can say that for this beam, it is going to be the same here, it's going to be the same here, it's going to be the same here. So to do that, all you need to do is select these beams. So just left click on the first one, then press Control and left click on the first. Okay. Then once you do that, you need to copy them. And to copy them, we said you go to the Edit tool, then you click on Move Stroke Copy. Then click on these intersection and proceed to copy them to the other positions that are similar. Okay, so let me do that. Okay, so then click there and there. And then once you do that, you have at least those beams in these directions. Then, as I said earlier, I just like to start with my primary beams. Those are beams that are being supported by columns. So I'll just do that, and then I will finish off with the other beams. And the reason you want to do that is so that your loads are decomposed as you wish. Okay, so you want your loads to be transferred from the beams to the columns. All right. So if you start with the secondary beams, you may not have what you intend to have as a load distribution method. Okay, you don't want, say, your primary beams are, are transmitting loads to cantilevers. So you want to ensure that the loads are being transferred whenever possible to beams that are directly transferring loads to columns. All right. So I think modeling in robot is quite easy once you get the basics of it, and then you have that. Yeah. So at least now I have my major beams. I can do this set here. Proceed to do this here. And then I have that. Then here at the top, I will proceed to place them. And we are good to go. So we majorly have the beams that we need, the major ones. So I'll proceed to create the secondary ones, the ones that are being supported by columns and beams, and the others that are completely supported by other beams. So to do that, I'll just click on beams here. Then I will place them. So just click on these grid intersections, then place them there. Then I'll do this here and proceed to place them there. Then proceed to do this here. Okay, then I will do the same thing here and the same thing here. All right, then I'll do the same thing on this other end. And then from this end there, I will place them in this direction here. And with that, I have majorly all the beams that I need. Okay, so I want to do two things here, and I want you to acknowledge this so that tomorrow you may notice the difference. So when it comes to partition walls, so say these minor walls that are carrying, say the walls used to partition, say the WC areas or the washrooms, sometimes you may want to just load the slabs directly because of ease of construction. Sometimes you may want to model beams. So that just depends on the engineers. Some the engineers will just uh, carry and design the slabs to carry the partition walls, and then some engineers will model the beam. So I want to show you or demonstrate both of them. So on the right, I'm going to model the beams, and then on the left, for this panel here, we are going to model the slab to carry this load. Okay, so I will start with modeling the beam, then we are going to model the slabs. So to do that, I think I may need another grid here. So from this grid to where this grid is, it's around 1310 millimeters. So I will track my grid 6. I'll go to my axis definition. And then along the X, where I have my grid 6, I will click on it. Okay, click on it to set it as the active grid. Then increase the number of repeats to 1 and have the distance as 1.310. Then just add the grid, then apply and close, and we'll have another grid here. So I use this to model my beams, okay? And you're going to notice one thing. I always start with the shorter grid, the shorter beam, then the longer one. And the reason for this is quite simple. Designing for the shorter beam, you're going to have less moments as compared to the longer one. So this one is going to be majorly like, if I started with this one, it would be majorly like a cantilevered beam from this end to this end. And it would give you difficulties designing for them. So it's efficient for you to first model the shorter beam, then carry the longer secondary beam with the shorter beam. I think that's just a more efficient way of approaching the design, right? So you have your major beams. So from here, I want to model the slabs. Let me see. Can I continue to around 10:15? We've just finished modeling the slabs and then we are going to proceed from tomorrow. Type A1 if that's okay. Type A1 if you're still here so that you can just proceed to model the slabs. Super. So again, I'm going quickly or I'm kind of rushing through because we only have 2 days together and I want us to cover as much as possible. So let's proceed. So I will continue to model the panels. It's really easy, but when it comes to modeling the panels, this is what I will always say about robot. Robot is very, I don't want to say user specific, but it gives you a lot of power as the user, okay? It allows you to control it as much as you want. Okay, so when it comes to modeling the beams, I always recommend you do this. And when it comes to modeling the slabs, I always recommend you do this. Work in one direction, maintain one direction of modeling. So if you choose to model from left to right, okay, if you choose to model from left to right, that is, you have your first click here, then your second one here, and your final one here, stick with that. Because the direction you choose first is going to be your major axis for the design of slabs. So the slabs themselves have something we call the local axis, and this is going to be the X, and this is going to be the Y. So the local axis, it affects how you interpret your results, okay? It affects how you understand your results. If you end up mixing them, understanding and interpreting your results may become a little bit difficult. So for, say, efficient and easy use of the software, I just recommend you maintain one direction of modeling. So this is what I'll do. I recommend you go left to right, then bottom. This is what I mean. So when you go to slabs, this is where you model, this is where the tool to model slabs is. Left click on the slab tool here, and then in the thickness, just click on this drop down, define the thickness, give it a name. So I will call this 150 millimeter RC slab. Okay, then you define the thickness here. So this will be 150, and then you define the material here. So this will be class 2530. Then I'll click on add and close. Then it has been added. So I just need to click on this drop down and select the thickness I added. Then we have the model, and the model affects how the softwares or how robot analyzes your slab. So because robot is a finite element analysis software, it has to break down your slab to small finite elements so that it can be able to design them. So for you to enable robot to do that, you have to select shell. Okay, so for you to be able to see the results from your analysis for the slab, you have to select shell. And then now for ease of modeling, always go with contour. It's a bit easier. Always go with rectangle. It's a bit easier to do. Then once you have that, just click on the points that you want to model your slabs at. So you just go from left to right, okay? And then to the final one here, all right? You go from left to right for all the panels. It may take a bit of time, but it's easier to do. Okay, so for all the panels, just go from left to right and then to the bottom. Left to right and then to the bottom. I realize I covered the space where we have our staircase with a panel, so I'll just delete that one later on, and we're going to model our staircase tomorrow. So for this one, I'll just place it here. And then notice I'm staying consistent, left to right, and then bottom. So just stay consistent with this, left to right, and then bottom. So let's recommend whenever you're using a software, just understand how it works, how it approaches things, so that you don't end up fighting with it a lot. Okay. Some softwares you'll end up fighting because you want it to work the way you want it to work, but it has a very specific way of doing things. All right, so always try research online, read the manuals from from Autodesk. If you're using Prota, just go through the manual from Prota, understand how it works. It will make your work easy because you won't end up having to fight with the software all the time. Once you understand it, it becomes a bit easier to use. Okay, I was missing that one. And then finally. And then with that, we have our slab, our structure rather modeled. All right. So that's how you model your structure. That's how you basically come up with a structure in Robot. And then in tomorrow's class, we are going to copy this structure upwards. And we are going to start with modeling the staircase, and then copying it upwards, and then loading it and designing it. Okay, so I don't intend to keep you past this time. I know most of you are tired, and I would also want to see you tomorrow. So just to say, keep things interesting, I will end the session at this point, and I hope to see you tomorrow. So thank you for joining us, and see you tomorrow.